Um, thanks for coming during lunchtime. This talks about Android rooting. It says Android 4.0. It's really about Android 4.x. And if you compare that to 2.x. Ice cream sudo make me a sandwich. Like he said, I'm an independent consultant. I used to work at Intrepidus Group. I was a senior consultant there and research co-director. Based out of New York City, I've done some past research in NFC, mobile wallets, NFC payments, like if you tap your card in a taxi cab or something, and some Bluetooth stuff. But today we're talking about Android open source project and OEMs, what the OEMs add on top of the Android open source project that we think of as one bundle of just Android. And then the consequences of what they've added, what they've done, kind of comparing that to stock Android. We'll cover some OEM-specific vulnerabilities in chipsets, some clever backdoors that OEMs have put into devices. And then we'll look at preloaded applications, and I'll show you guys a tool that I wrote for kind of getting a quick overview of what's on a device. Just to be clear, these aren't 0 days. Can you guys see the slides okay? They look really dim to me.
Yes.
I don't think increasing my brightness setting helps.
That's
Okay. Since it's such a small group, if like something's unclear, just stop me and ask a question. Yeah, so just to be clear, these aren't vulnerabilities that I'm releasing now, and a lot of them aren't even bugs that I've found. They're just really great examples of what not to do. And the devices that I'm going to be using for a demo, I got these 3 devices from China Mobile. I had a friend in China, and he brought them back. And I bought a prepaid SIM, so they're on a network here. But they're really cool, and they've got good examples of what we're going to talk about. So Aosp, I'm going to use it throughout the presentation, is the Android open source project. And it's what we think of as Android. It's comprised of the Android kernel, hardware abstraction layer, which is like a system service, and then a hardware abstraction layer definition, and then all the system services. So it's up to the OEM. That's like the original equipment manufacturer, Samsung, HTC, Huawei, whoever, to implement that HAL code and the drivers for whatever hardware they want to put on the device. So Aosp can be like checked out and just built for several devices, Nexus 4, 7, 10, all of the pure Nexus devices. Other devices add on top of that, on top and below. So that's the portion that we're going to cover, not the Android open source project itself. On the right here, you can just see some examples. This is just from Google's website. Like Wi-Fi, the company is Broadcom, and that's a proprietary driver, proprietary interface to Google's HAL that they have written. So Google's not responsible for that. The OEM or the manufacturer of the chipset is. Some background on device components, just so that we can cover how the devices are actually rooted. The first part is the bootloader. That's the first thing. That's the code that gets loaded when you turn on your device. And its main job is to, well, first boot your device, but security-wise to ensure that only signed code can be booted. So that's either signed by the carrier in some cases or the OEM. There's 2 ways to unlock the bootloader to stop it from booting that signed code, which is what you want if you're installing custom ROM or doing anything to modify the device. There's developer unlocking and exploit unlocking. Developer unlocking is a term and exploit unlocking is not, but I'll define them as we go. And that's where we've been seeing a lot of 4.0 roots come from. The Android open source project bootloader is fast boot, so you may have seen fast boot. It's got a ton of capabilities, and usually what carriers will do is modify fast boot and strip out some of the capability to flash directly to the file system. The recovery partition, you may have heard of Clockwork Mod recovery, Team Win recovery project. That'll allow you to write to the file system as root pre-boot. So you can boot into the bootloader and the normal boot process, or you can boot into recovery and access the system image pre-boot. We'll look at some of the file systems and permissions, which is another kind of surprising place that a lot of the root attacks come from. /system should be mounted as read-only. That contains some binaries. Data local prop was pre-4.2. I've been looking through the source tree and trying to figure out when exactly they started ignoring that. I think it's 4.2. Default.prop is the replacement. So even on post 4.2, if you put in a data local prop directive, ADBD, the Android Debugging Bridge daemon running on your phone will ignore it. And then we'll look at Symlink attacks. Like we said, bootloader allows booting unsigned code once it's unlocked. There's a bunch of different ways you can tell if it's been unlocked, and a bunch of different ways to unlock it. So HTC, you probably remember S-on and S-off from like the early days of the HTC Evo and all the cool like 4-inch screen smartphones. There was unrevoked, I think, which was a permanent S-on, S-off. You don't need to do that anymore. You just need to unlock the bootloader. HTC has broken it down. So S-on and S-off. S-on protects HBoot and the radio, which you don't care about if you're writing a custom ROM to /system and a custom kernel. Next, excuse me. Nexus is just Google with a lock-unlock symbol. You've probably seen that on your Nexus devices. And then Qualcomm secure boot enabled, disabled. So two very different scenarios for unlocking the bootloader. The first one is developer unlocking, where it wipes /data, which is all of your personal private data, and then exploit, where it doesn't wipe data, and it would allow someone to gain root that way. So when a bootloader is locked, this is what it looks like. On the left is an HTC. You can see it has both the locked and the S-on flags, and then on the right, you can see, I don't know, it's a bad picture, Samsung official, and Qualcomm secure boot enable. So that's how you know those bootloaders are locked. So if we were to unlock a bootloader via an exploit, it's probably not going to wipe the /data partition and leave your personal data on the device. So unrevoked is an example of that we mentioned before. That was HTC only. Moto Chopper is a Dan Rosenberg exploit. And it was named Moto Chopper, I think, because he found it on a Motorola device. But it works across lots of different devices. And it's a chipset-specific vuln that we'll cover later on. Odin is a leak tool from Samsung that allows you to flash a system image. And then Heimdall is the open source implementation. Uses the same protocol, but it can be updated like an open source project. So all these the data partition is not cleared. So these are the exploit unlock examples. If you wanted to developer unlock your bootloader, which is supported by a bunch of OEMs, HTC Dev, I think, was the first one. It just uses fastboot. You feed a device identifier token to the HTC website, and they come back with a device token. You feed that to fastboot, and it unlocks your bootloader, and it wipes /data. So an attacker couldn't do that to get access to your data. It's HTC sanctioned. Some of the carriers, I think, have asked HTC to take their devices off. So if you have a device that you bought directly from HTC, you're going to be able to unlock it this way. If you went through the carrier subsidy program, maybe you can't. Now Motorola does the same thing. Once you've unlocked them either by exploit or developer unlock, you'll see this. So on the left, you can see it still says S-on, right? It's protecting HBoot in the radio. But now you can flash unsigned code to the system partition, or the boot partition, or recovery partition. It says unlocked on the top. And on the right there, custom, and secure boot is still enabled, which is a similar thing to S-off. An OEM bootloader unlock is super simple. This was on my Nexus 7 device. It's the same command as HTC, but you don't need to feed it that identifier token. You just unlock. You get the screen on the right. Unlock bootloader may void warranty. You're going to wipe all your data. Yes. And then on the left, you can see lock state unlocked. It's really simple to do it the developer way, more complex to do it the exploit way. Once you've unlocked your bootloader, it means that unsigned code can be flashed onto your device. So you probably want to relock it after. And this is something that I don't think I've ever seen on instructions for a rooting attack, is actually relock your bootloader. If you're using fastboot, it's really simple, right? Fastboot OEM lock. Obviously, it doesn't wipe your data to go from a less secure state to a more secure state. On the right, now it's locked. Once you've unlocked the bootloader, though, you still don't have root. All it does is actually, it's the first step, right? It lets you flash the unsigned code. So the next step is usually to flash a custom ROM or a custom kernel if you really want to, or a recovery image. So the recovery image is super useful. Like I said before,
Sorry, just one quick question. If you relock, does it not check the signature then?
no, it's not going to then like kick off whatever has been on there. Unlocking it lets you write unsigned code. Locking it doesn't check if the code that's written there is signed.
Okay.
So the recovery image is super useful. Lets you access the file system as a low-level user pre-boot. So you can write a root binary to the device, or you can back up the device, do device imaging. So it's really, really useful. And that's a way that we see a lot of rooting attacks take place. Okay, finally we have root. But what does root actually mean? On an Android device, since it's Linux-based, all it is a binary with a setuid bit somewhere on the file system. So obviously you need root to put that binary on the device. But once it's on there, anyone who can execute that binary gets a root shell. The other option is debugging route. So this is supported by the Android debugging bridge daemon. And if it sees one of these directives, the daemon will give, will give the whoever connects to it a root shell. So that's not something that that applications can use. That's going to be only for Android debugging bridge. Okay. So because it's just a binary, it's a standard Linux binary, it's pretty hard to detect. So we've seen a lot of applications look for evidence by looking at superuser.apk, seeing if that's installed, or some of the other superuser managers. Systems mounted as read-write, if there's junk in data local temp, where a lot of kind of one-click roots will leave remnants. And then in system, there's bin and xbin. If there's the SU binary there, a lot of applications will then detect root and say you can't do X, Y, or Z. You could set it as the same name as an existing setuid binary on the file system. I don't know what problems that would cause. I always just name it blah, and nothing has ever detected root. So I just keep it where it is, set it to blah, and then you can see there, blah is my new root, my new SU. All right, so we're gonna, is that section cool? Okay, so we'll cover the kind of overview of the 4.0 roots that we've seen and divide them into 3 categories. The drive-by roots, which are really bad, the user-initiated roots, which are kind of bad, bad for carriers, not so bad for users if you're careful, and then the data wiping roots, which are really necessary for developers to access their devices. So the drive-by roots, something that if you left your phone at a bar, if someone had 5 minutes with it, or if, something that you wouldn't know the device had been rooted, maybe there's malware. If you leave pre 4.2, if you leave ADB enabled on your device, anyone can connect to it, and that opens up a lot more pathways for the drive-by roots. So we're going to assume that you haven't done that. Post 4.2, there's the signature checking, so you have to authorize per computer. So if you have a secure lock screen, and someone takes your phone and plugs it into their computer, there's going to be a pop-up behind the lock screen that says, do you want to authorize this computer? And if you don't interact with it, the computer doesn't get debugging bridge access to your device. So we're assuming that that's either the case or ADB has been disabled. User-initiated roots, you're going to have at least some idea that your device is rooted. It may require multiple reboots. Some can be really simple, some can be complex. It has the possibility of bricking your device, and something that would be too difficult for malware to do. So you're going to know that your device is rooted here. And then data wiping roots, which is bootloader unlocks, right? or reflashing. Some of the Odin attacks would actually reflash the whole device. These are the ones that we're not particularly concerned with. They're not a valid attack vector. All right, so Android 4.0 is why that talk is called 4.0, other than ice cream sandwich is a great name. Introduced on-device encryption. It fully implemented ASLR. There's ASLR pre-4.0, but this fully implemented it. There's DEP, and it makes it much harder to write local exploits. So we saw the local exploit count just kind of tail off. So pre-4.0, there were a ton, right? Like it seemed like every 2 weeks someone had a new local privilege escalation exploit. You plug your phone in ADB, run some script from some random dude on the internet, and then you get a root shell. But post 4.0, we've seen like one-ish, right? We saw the ADB recovery arbitrary file write vulnerability that could be leveraged to give you root. And then we saw master key vulnerabilities 1 and 2, but I'm not really counting those because those really affected the whole source tree like pre-2.0, right? It was a vulnerability that went way before 4.0. So really one universal Aosp is responsible for this piece of code, root, that we've seen. So how are devices getting rooted? How are their local privilege escalation exploits? Well, I mean, the short answer is it's all in the OEM components, right? All in these third-party drivers and in the carrier components. So we're going to go over some of the cooler ones, some of the hardware-specific privilege escalation. So there was Exynos, probably saw Exynos abuse on XDA, Moto Chopper, which is Qualcomm chipset-specific, some really clever OEM-specific backdoors. So ZTE had this hard-coded password on a binary in their device that would just give you root. LG has a much less public one. And these are backdoors where like the OEM now has access to your device. It's just like for their techs or whoever, or a consumer to just root the device without launching an exploit. And then some OEM file system permission issues. So I have a device that I've since bricked, but I'll kind of walk through rooting that one. The OEM responsibility, so this is a Google diagram. And you can see the middle layer there is the hardware abstraction layer. So there's camera, audio, graphics, and other HALs, hardware abstraction layers. So that's how your piece of hardware is going to interface with the Android operating system so that it's transparent to the user, right? You may want to use a different camera. Well, you're going to have to supply the driver for that camera, and it's going to have to fit Android's HAL definition and interact with their system service. So there's an API for that. So we saw the list of drivers available for the Nexus devices, but on a device like, I don't know, this device, maybe there's like 25 different HALs that they're interacting with because they want their own hardware to interact with Android. So the first of these attacks is Exynos. So real briefly, Exynos is a ARM-based system on a chip manufactured by Samsung. So it was in almost all the Samsung devices. So this was a really widespread attack. It was on this particular type of processor. And the issue was, while they were creating their driver, Samsung kind of used a shortcut and mapped /dev/Exynos mem to all of physical memory. So it was really easy to like go through, flip whatever bit you needed to flip. So someone wrote Exynos abuse, this guy Aleph Zain, right? And it was like a patch. So I should have switched the order of these. But the bottom one is what it looks like if you just list that memory. And the top one is the patch, right? And that's how it really should be. Only system can read this memory. And the real patch is like a kernel level patch, right? Where you're not mapping all the physical memory to a public device driver. So Samsung has since issued that patch and the issue is fixed. But it was just a perfect example of OEM hardware that allowed you to root your device. Moto Chopper is a Dan Rosenberg root. He's done some really cool stuff. His name's, I'm sure, come up if you've looked at Android stuff. It was a really, really complex exploit that he made really simple. and it's an ARM trust zone exploit, and it unlocks the bootloader and then flashes unsigned code. So it worked across a ton of devices. Like I tried it on a couple of these. Samsung, Motorola, Huawei. It's just called Moto Chopper. Yeah, that's the particular chipset that it affects. And I'll put these slides online. They already are online on my GitHub now. The LG backdoor one was so cool. It was such a perfect example. And it didn't really get a lot of publicity. So I followed the directions, rooted my LG device, and then pulled the ADBD that I keep talking about. I pulled that off the device and threw it into IDA. So credit for this goes to his name that I'm not going to say. So yeah, just to clarify, LG doesn't have access to your device. It just lets you as the local user get a debugging route prompt. It doesn't put an SU binary on you getting debugging route. If you wanted to, then you could put the SU binary on and apps could access it. So I'm not an assembly code expert, but I threw it into IDA, and it's pretty simple to see what's going on, right? It looks for that file. It tries to read it. Blah, 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 blah. Check LG official, enable root at the bottom, right? Like super simple. So all I did was, well, here's an example. List that file, it's not there. Touch it, doesn't have to have anything in it. Restart USB debugging, check, uncheck on the device. ADB shell, ID in your root. So.
Does that work on Nexus 7 as well?
No, so this is LG specific. So there's the ADBD binary that sits on the device. It's part of the Aosp.
Okay.
LG modified it
Okay.
and added this in and then shipped it. So this is a specific LG device. Actually, I think it's the Optimus G maybe.
Okay.
And I think it affected some earlier builds also. But like really simple, right? You don't have to launch some weird rooting exploit against your device. You get root, so you have control over your device. Really kind of a nice exploit. That one's not so bad. There's a new root. I guess this was a couple months ago by JK's called LG Pwn. So I'll harp on this later, but LG makes a backup app. So this is one of those carrier apps that doesn't need to be on the device because Android does backup, right? There's the Android backup app. So there's a race condition in this app. He was able to locally exploit it. And you could potentially leverage this vulnerability to the point where it's a drive-by root, where if you have access to someone's phone for a minute, you plug it in, you root it, you install whatever you want on it. So this was a really bad one. First one, not so bad. This one was pretty bad. This ZTE device was just a cool device because it basically roots itself. So there's the bootloader, there's recovery, and then, I don't know, ZTE added FTM mode. I guess it's factory test mode. So power and volume down, you boot into FTM. So this is how it should work. Go to data local, you can't list it out, right? You don't have execute permission on the directory. How it works in FTM mode is that you can list it out. So data local temp is the area of the file system where you can write to anything. Everyone has read, write, execute, I think privileges. Because of that, so if you can list out data local and you have execute there, you can do symlinking, right? So data local temp gets its permission set at boot time. If you can symlink that to say /data, data is going to get the permissions intended for data local temp. So you symlink it, you reboot, data is getting the permission for data local temp. Now you can write into /data. So the two issues are one, FTM mode, like why is that there? And the second one is that the init script is not checking if data local temp is a symlink before it's setting permissions. So we went over some of the directives that give you debugging route. You can just echo ro kernel qemu equals 1 into data local prop, right? Because it's a pre-4.2 device. Reboot it, ADB shell, and then you can see the root prompt at the bottom. All right. So moving beyond the OEM additions to the operating system layer, and moving on to like up one level to the default applications that are on your device. So like, what is actually on, maybe not your Nexus device, but your carrier device? Since I recently discovered that Vizio is so cool, I made this little thing. So you have the Android open source project at the bottom, and that's green because it's been audited. It's obviously on every single device, and we're not seeing that many more bugs with it. Maybe there will be more bugs later. Then you have the Google apps, right? Gmail, Maps, YouTube, SMS, etc. Those have been pretty well audited. They were made by Google, who should understand Android security, etc. They get audited. Then the next level up should be like yellow or like orange. Watch out. You have the OEM apps, right? The backup apps, the LG backup app, etc. They might put games. The really crucial thing about these apps is they're stored on /system, which is a read-only file system. So you can't remove them without rooting your device. System/app. All of your applications go in /data/app. Data is read-write, and you can uninstall those apps. So you have the OEM apps, and then on top of that, you have the carrier apps, right? So you may have a Samsung device. Samsung puts their apps on it. It gets shipped to AT&T. AT&T puts their apps on it. It gets shipped to T-Mobile. T-Mobile puts their apps on it. So now you've got this like conglomeration of apps on your device. And then you have your apps on top of it. So maybe you rooted it and you use some third-party tool to root your device, and now that's just sitting on your device. You don't really know what it does other than root your device. So it turns your sleek little Android man into Jabba the Hutt. Now he's got all these apps. So I made a quick little tool. And maybe I'll start the demo of it now, because it can take a little while. Made a little tool to just real simply plug in your device, pull some apps off, decompile them, look at the endpoints to see what they're really doing. Right? It looks at the Android manifest file, which gives you a ton of data about an app's intentions and its privileges. So, oh no, whatever. Okay, so I've got my China mobile device here so that I don't offend any US carriers. So you run the tool, it gives you this nice help dialog. The options that I want to run, I just want to filter for ZTE named apps. So that'll be in either the path name or the class name. And I want to decompile them, and I want to grab them off the device. So all I've done is like plugged in the device and just run this. So it's going to go ahead, make a folder called ZTU817. It's going to get them, and it's going to start decompiling them. So while that happens in the background, because it can take a little bit. Oh, cool. OK. So we'll go over all the IPC end. It's just switching back and forth now. OK. So all these intent filters and IPC endpoints are declared in the Android manifest file. It's a really handy file for getting the gist of an application. So what the tool does is just look through them automatically. Okay. So we'll go through the four. The first one, and the one that we find the most bugs with, is really interesting, one is a content provider. So content provider is Android's interface to a database or a file. You access it with content : / and then the authority. So when you see it declared in the manifest here, provider, blah, blah, com, Huawei, high disk provider, dbank. That's the authority. So content : / authority is going to allow you to query that content provider and see what it supports, be it a database or a file. Activities are what you see on your device. It's an interactive screen. It makes up the application UI. And it can contain an intent filter. So it can be launched using an intent from ADB or from another application. So that allows you, like if you have an app and it says, like, look at your contacts, and you hit the button, it'll pop up the activity for your contacts. It may not have access to all of your contacts, just whichever one you select, right? Services are a separate PID from the application. They're designed to run even if the application is backgrounded. So maybe your music player runs the music in a separate service. broadcast receivers are intended to, they'll receive an intent that's broadcast to every broadcast receiver on the device. So the broadcast receiver registers with the operating system then knows to pass that broadcast on to the appropriate broadcast receiver. So the protections for these endpoints are pretty general. You can set a permission on your Android manifest file at the top level, which will propagate down to every endpoint. So you need this permission to interact with this application in general. So we don't see that a lot because typically applications want to expose 1 or 2 endpoints. You can set a permission on the particular endpoint, or you can choose to not export that endpoint. So pre 4.2, all the components were exported by default if there was an intent filter, because having an intent filter there indicated that you want other applications to send intents to your application. Post 4.2, components are not exported unless they have an intent filter. So you can just always explicitly set this. Like, it's much simpler to just say Android export equals false if you don't want to export this endpoint. Content providers specifically can have permissions. They can have a read permission on the database, a write permission, and you can set export equals false. Activities, the same thing. Permissions, export equals false. Services are the same. Receivers are a little bit different because any app can register, but then whoever sends the broadcast specifies the permission needed to receive that broadcast. So then it's on the sender, not the receiver. And again, you can set those to export equals false if you just want to broadcast within your process. So one of the major problems that we see with the preloaded applications is permission leakage. So these applications are on your device. You can't uninstall them. They've requested permissions at install time, which you didn't control. And they may leak those permissions. So for example, everybody has a weather app on their phone and you don't know where it came from. Maybe it requests GPS and Wi-Fi permissions. Obviously it's granted those because it's on your device. And say it has a content provider and an activity. And when you launch the activity, the weather app comes up, it reaches out to GPS, says, oh, okay, now I'm in Austin, Texas, let me update the weather for Austin, Texas. Well, that's great and it's harmless in and of itself. But say you also have a content provider, and that content provider is meant to provide city-based weather to all other applications, right? So that's unprotected. So if you can launch the activity, update GPS, and then access the content provider, it's going to say Austin, Texas. So if there's a malicious party on my device, they now have access to GPS, which without me explicitly granting that, right? This is a really simple example. People have written papers on like much more complex examples. So a real-world permission leakage issue in like about a year ago, right? The Android SMS receiver service exported a receiver with no permission restrictions, so any app on the device could send out a broadcast and it would look like you're receiving an SMS. So it's perfect for like smishing, phishing. Oh man, 5 minutes? Okay, so I'll move on to the tool. I don't take any responsibility for the name. I did this work at Intrepidus Group and it was a crowdsourced name. And someone picked Manifest Analyzer, Analfest, and it stuck. I can't get rid of it. So the point of the tool is to just grab whatever from the device, decompile it, and then parse through all the manifests as a whole, right? So you're going to look at all the permissions that are declared by the custom applications. The objects are going to inherit from each other, right? So each child is going to inherit from the parent, is going to inherit from parent. So you get a pretty complete view of what's accessible and what's not, and then it spits out an easy way to query that particular endpoint. For the content providers, Drozer is still like a great way to do it. Okay, so I have 5 minutes. I'm going to kind of zoom through this, and then we can do Q&A after. So on this device, there's a notes provider. So you can like type in your secret notes to yourself and save them. It also exports this content provider with no permissions. So if you query the content provider, you get all of the notes. As you can see, yeah, my secret note. Okay. All right, so it went off and grabbed all the APKs called ZTE from the device. And didn't find a ton of interesting stuff, right? We have one unprotected content provider here, no hidden codes, menus, debuggable apps, and a couple applications that share a UID. So that means that any bug in an endpoint on one of these affects the other one. So before we go on, let's just like pull email. So this is any application called email. We get a couple more interesting things, right? A permission called read attachment that's just more dangerous. And then a permission called access provider that actually requires a signature. We can pull, what else do we want to pull? SMS. This is not pulling the SMS messages, by the way. This is pulling applications which interact with SMS. Okay. So now that we have some context for this, content providers look like that. You can see the exported content providers. Services, kind of the same thing. It'll spit out the shell command that you just copy and paste into a shell to launch the service. Activities, same thing. If you want to actually go deeper into this, you can reverse the app, see where it's actually handling the intent message that you send it. So here it's in get intent, and it's looking for a string extra called path. So if I send an intent that has extra string path and I mount SD card camera, I can launch the activity directly. So that might be interesting for fuzzing, et cetera. You can just launch the activity with an argument or an extra string that it will parse through. Receivers, this is not my bug, but it's such a fun bug. This was on, so Quark's lab did a talk picking on one particular OEM. Some of their code would just pass a parameter to the shell. So if you send a broadcast with a particular action, the intent filter gets triggered, and it handles this code, so they were able to just send the output from the legitimate command to dev null, and then they just did an example of system bin ID into a file on the SD card, and then you can read that. You can see there, if you cat SD card shell escape, you get the results of the ID command. So that was command injection from a broadcast. Okay, is that 2 minutes for the talk? Okay. So I'd harp on this later. Just basically, as an OEM or a carrier, don't reinvent the wheel. Google has a secure app store, provides a Wi-Fi hotspot, connection managers, etc. There's no need to create a third-party application to do that. Some examples we found in app stores basically allowed you to man-in-the-middle app purchases, decompile the app on the fly, inject a reverse shell into it, recompile it, send it down to the user, and the user had no idea that it was now signed with your key because for a third-party app store to work, there has to be unknown sources checked, which means there's no signature checking on the app. So be safe and use Google Play. Shared UIDs are particularly bad if you find a bug in one of the IPC endpoints because it can affect all the other applications that also share that UID. So if they share a system UID, even worse. So point is, Aosp can be super, super secure, right? Implement all the security in the world, but until OEMs and carriers increase the security of their applications and audit their applications, devices will keep getting rooted. What can OEMs do? Don't modify Aosp. Duh, that's not going to happen. Patch vulnerabilities and deploy quickly. Don't bundle a ton of applications. Put them in data app instead of system app so the users can remove them if they don't want Roller Coaster Tycoon. And use Select Bootloader. MNOs can vet the preloaded applications. They can help the OEMs quickly push a patch, right? If Samsung comes, Anyway, don't reinvent the wheel. And what can you do? You can install CyanogenMod if you want to, right? You keep your device up to date if your carrier allows you to and the OEM allows you to. Don't root your device. If you have to, hide it. So the coolest thing here, I think, is granular patching. So I've heard some talk about this, and there's an app I think by Colin Mulliner and John Oberheide called Rekey that will, if your device is rooted, it will patch other rooting exploits. So that's a really cool project. Google's maybe going to do something. Anyway, that is all I have time for. On that GitHub are the slides and AnimalFest. Again, I did this work at Intrepidus. I recently left there, so I need to thank them for the work. But yeah, feel free to tweet at me or email me. I know I had to kind of zoom through that last third, so sorry about that. All right, is that the end? We have questions? Okay, we're out of time. Well, I'll be out in the hall. Cool, thanks a lot.